we move to the second speaker of the session, Stuart Parkin, who will be talking about racetracks now in 3 dimensions. Thank you, Stuart.
Okay, well, thank you very much for the organizers for having invited me here to give a talk. And I'm going to talk about racetrack memory, but I want to talk about a little bit about cryogenic racetrack memory. First, I'm going to introduce what is racetrack memory. Then I want to talk a little bit about some of our work, recent work, on particular some novel superconducting effects, in particular something called the Josephson diode effect. This picture, you can see some of the laboratories we built over the last few years since I moved to Germany. And in this laboratory, we have a long vacuum tube connecting multiple deposition chambers, so we can combine different techniques to build complex systems with interfaces. Mostly, I'm interested in interfaces. We heard a very nice talk from Claudia about bulk materials. I want to show a little bit about how we can use interfaces to imprint properties of one material on another material. And you can see here, these are my co-workers, postdocs, and students in my group that have contributed to this work. Oh, this goes forward. Okay, so what is racetrack memory? You heard before how we need to use, we're consuming more and more energy. Much of that energy is going towards storing digital data. And today, digital data is still stored, 70% is stored in magnetic disk drives, a 70-year-old technology that has benefited from a spintronic device that I helped to invent a few years ago, enabling enormous increases in the storage capacity of magnetic disk drives. But just like Moore's law for computing devices, that ability to increase the capacity of magnetic disk drives has come to an end for a variety of technical reasons. We need to find another type of device that could take over from magnetic disk drives with improved performance and capacities. And in my mind, the single way to do this is something I called racetrack memory. So if you look in this foil, you can see on the right-hand side, you can see a cartoon of a vertical magnetic nanowire in which we store information as the boundaries between magnetic regions, shown here as blue and red, magnetized in opposite directions. And on the nanoscale, the boundary between two magnetic regions is called a magnetic domain wall, and this has many properties of a particle. It has momentum, for example, it has mass, and it behaves in very interesting ways. So my concept is that in this vertical nanowire, we could store perhaps 100 of these domain walls. And a magnetic bit, a digital bit of information, would be the presence or the absence of that domain wall. More importantly, we want to move all that information around the racetrack. So this is unlike any other memory technology today, where the information is static. For example, in a dynamic random access memory, you have a capacitor where you store a certain amount of electrical charge. Here, however, the information is moved by passing currents into the racetrack. And I want to show you how we can do that. The currents can give rise to spin currents, and when they cross an interface from one magnetic layer to the other, those spin-polarized currents can deliver angular momentum, providing torques that enable the domain walls to move. And we've demonstrated speeds of these typical domain walls exceeding 1 kilometer per second. And that means we can build devices which operate at deep sub-nanosecond speeds. The concept is you then use currents to manipulate synchronously all of the domain walls, and we move them to individual devices within the racetrack for writing or reading that information. Now, I don't really have the time to discuss in detail the physics of racetrack memory. I've actually worked on it since I first proposed it in 2002, and during that time, we've discovered entirely new physics that makes it actually even more interesting than when I first proposed it. We can move the domain walls with current pulses 10 times more efficiently than was possible 2 decades ago. And this is what I call, we've gone through different versions of racetrack over these years, and each time with new physics that make it very interesting as to the manipulation and motion of the domain walls. Now, the most interesting version is this version 4.0. And on the magnetic nanoscale, all little magnets, as you know, have stray fields. And those stray fields will cause interactions. So for example, if you have a magnetic heterostructure with two layers, one on top of each other, on the nanoscale, if the layers are parallel, they will automatically be antiparallel through these stray fields. On the other hand, if they're magnetized perpendicular, they will automatically be organized in a parallel fashion. So you have to avoid these stray fields. So I invented, many years ago, a concept I called a synthetic antiferromagnet, in which case we take, in this case, for racetrack, we take one racetrack, and on top of which we build a second racetrack separated by a thin layer of a particular metal. Here it's ruthenium. There are some other metals we could use, which gives rise to strong antiferromagnetic coupling through a long-range interlayer coupling, RKKY coupling through that material. This means, as you can see, a red region in the lower racetrack, which is a magnetic heterostructure, would automatically be a blue region in the upper racetrack, and we can design the two so the net magnetization goes to zero. There are no stray fields. And it turns out when we did this, we discovered that this giant antiferromagnetic exchange field itself gives rise to large torques that enable these domain walls to be moved even more efficiently. What does that mean? That means if we take this ruthenium spacer layer and increase its thickness by just a few angstroms, the coupling strength changes from antiferromagnetic to ferromagnetic. That 3 angstrom change in thickness would mean the domain walls would travel 10 times more slowly in the same structure where the two layers are coupled now ferromagnetically rather than antiferromagnetically. So this is racetrack. So today it looks like a very exciting technology where we could store very densely information and we could manipulate the information, read it and write it at speeds that would enable us to improve the performance compared to a magnetic disk drive by 1,000,000 times. In terms of speed, 100 times in terms of energy efficiency, and form factors would of course be orders of magnitude smaller. So just give an example. So how do we, most of the work we've done over the last few years is in nanoscopic racetracks, but they're typically microns wide, so we could use photons, optical techniques, to detect the polarization of the magnetization. So we shine a light, a polarized light plane, and when the light is reflected from a magnetic material through a Kerr effect or Faraday effect, the plane of polarization is rotated, and we can then detect the magnetization. So on the right-hand side, you can see a domain wall. In this, let's say here is a racetrack. It's 1.7 microns wide. The black region, the magnetization points towards you, the gray region away from you. This is the image, the optical image. We apply a current pulse or several current pulses, nanoseconds long. The domain wall moves from here to here, and then we can detect it, and we can detect the velocity of the domain wall. What we wanted to do here was to show, as we reduce the width of this racetrack, this horizontal racetrack, from 1.7 to 1.4 to 1.1, all the way down to 200 nanometers, we can detect that optically, even down to 200 nanometers in width. And surprisingly, we found that the current-induced motion was essentially independent of the width, whether it's 2 microns all the way down to 80 nanometers in width, which is technologically relevant. And of course, a characteristic feature is that the domain walls will move here. They're moving at 150 meters per second for these current densities we're putting into the racetrack. And there typically is some critical current density below which the domain walls do not move. Theoretically, there should be none. That is caused by variations in local anisotropy and magnetic properties within the material itself. Nevertheless, we can then explore ways in which we could improve the materials that are forming this racetrack, and we're interested in engineering things on the atomic scale. So here we've shown, here is a racetrack. This is the magnetic material. Underneath we have a heavy metal, HM, which is formed from, for example, from platinum. When you pass a current into a heavy metal, then the current becomes spin polarized through a phenomenon called the spin Hall effect. So this spin current generated by converting electrical current into spin current will then diffuse into the magnetic material, and the spin current carries spin angular momentum. It will cause torques on the magnetic material, and this is how we move domain walls. We've shown that by introducing what we call dusting layers, 1 angstrom thick, this is the length scale, we can dramatically influence, for example, that critical current density, and we can also dramatically influence the velocity of the domain walls at a particular current density. So you can see that these interfaces and how the current is generated and crosses the interface from these heavy metals to the magnetic layers providing these torques plays a very critical role. So unlike the bulk materials that Claudia is talking about, we're talking about atomically engineering materials, one atomic layer at a time. And the typical racetrack material here is formed from a nickel-cobalt sandwich. Each layer is just a few angstroms thick. So the racetrack itself is basically 1 nanometer thick magnetic material, a ruthenium layer, which is 0.7 nanometers, and another magnetic material, 1 nanometer thick, all combining the layers on the atomic scale, which we could engineer or try to influence the physics to make the domain walls move more efficiently. And of course, we can move them very efficiently, as shown on the right-hand side. And I just wanted to show recently what we've demonstrated. Instead of optical techniques, we can build into a racetrack, we can build whole sensors. So this is the racetrack. This is this region. It's 73 nanometers wide. And on the sides, we build into that heavy metal layer here formed from platinum, we can build these extended wings. And this is where we measure the local voltage, the Hall voltage that is generated by passing a current into the racetrack. And we can actually detect then the individual domain walls, or in fact, a series of domain walls created in a particular racetrack by simply measuring the signals from a series of these Hall sensors we built into the racetrack. And it turns out very interestingly that one sensor can detect the position of a domain wall here, but also far away from the sensor if we properly design these sensors, something I don't want to discuss. Nevertheless, we can then see, so the Hall voltage, of course, depends on whether the domain is pointing up or down. This is how we can detect where the domain wall is along the racetrack. And on the top, you can see an individual domain wall that is moving along the racetrack by a series of current pulses, and then we change the direction of the current, it will move back, and the whole signal, you see, increases and decreases as the domain wall moves incrementally along the racetrack. And we can show that we can position the domain walls at these Hall sensors very precisely because the current density here is slightly reduced, so the domain walls slow down. So we can position them at these Hall sensor points. And if you look on the right-hand side, you can see we can position the domain walls with an accuracy of about 30 nanometers, spaced about by about 100 nanometers. All of these numbers are exactly the technologically relevant length scales that we need to build a real racetrack memory that could compete with a magnetic disk drive. So we think this is a very interesting development where we've shown the ability to create racetracks even down to a few tens of nanometers in width with the precision of positioning domain walls on the scale of a few tens of nanometers. This is something we've just done recently. Well, originally I was going to say more about three-dimensional racetrack. I'm not going to say too much about that, but we actually have several projects to build a racetrack, one of which I was very interested. Robert Hoy gave a very nice talk, and he discussed a company he's formed to develop advanced forms of atomic layer deposition. So we are attempting to build this racetrack with these atomically thin metal layers by atomic layer deposition. And we think we've almost succeeded in developing such techniques, which means we can build racetracks on vertical walls and therefore build real three-dimensional racetracks, according to a patent that unfortunately is no longer relevant because we filed that patent 20 years ago. Nevertheless, finally, we might achieve what we had proposed we could do in that patent many years ago. Well, another technique that one of my students, Kei Ge, used to build a three-dimensional racetrack is very interesting. It's a technique in which we use a soluble oxide layer. This here is shown strontium-3, aluminum-206. This is originally developed by Harold Wang at Stanford University just fairly recently, a few years ago. So we take a single crystal substrate, here it's magnesium oxide. We grow a layer of this strontium aluminum oxide by pulsed layer deposition techniques, and on top, using sputtering, we grow our atomically engineered racetrack material. Then we dissolve this strontium aluminum oxide layer completely from the edges of the substrate, which is in this case 1 centimeter by 1 centimeter in width. We dissolve the oxide layer and float off a membrane that contains this atomically engineered racetrack, and we float it off and manipulate it onto a surface in which we've pre-patterned. This is a sapphire substrate, and I think you can see this is a hillock. We call it a hillock, and you see this black line. That's the cross-section of our membrane with the racetrack on top of it, which Keigu has placed on top of this hillock. So effectively, we've created a three-dimensional racetrack. And when we submitted this paper to Nature Nano, the referee said, great. Originally, hillocks were 300 nanometers tall. He said, well, the editor said, we should demonstrate 1 micron tall hillocks. And Keigu was able to do that. And then he found, if you look on the right-hand side here, the velocity of the domain wall as a function of current density with a threshold current density. The blue curve is the freestanding membrane, and the green curve is after we've draped it over a 900 nanometer tall protrusion, and you can see the velocity versus current density is the same. So effectively, we've been able to build what we think is the first really three-dimensional racetrack in this form. We think it's quite elegant, and as I said, you can see that this racetrack really is almost following the contours of these hillocks as shown here. Well, now, Claudia gave a fantastic talk on Kugome systems, and she mentioned this material, manganese-3 tin and manganese-3 germanium. So I don't need to introduce it, but it's a super interesting system because it has a chiral structure, antiferromagnetic structure, where due to frustration, you get a so-called 120-degree structure as shown here. Oh, here we are. You see these are the manganese on these triangles, as Claudia discussed, separated here by tin. And this Kugome lattice has many interesting properties, but the one we want to focus on is the fact that this 120-degree assembly of magnetic moments has a chirality. Even in a single monolayer, it is chiral. It's a very interesting non-collinear spin structure, and I don't want to discuss that in detail, but we want to use it to explore explore superconductivity. So I want to talk about proximity effects. Here we want to impose superconductivity, let's say here on a ferromagnet. So what happens? A superconductor, as you know, typically consists of Cooper pairs. They form the condensate in which two electrons will have opposite spins and opposite momenta. What happens if we take a superconducting material, let's say niobium, and we place that niobium in proximity to a ferromagnet? This was considered by Bozdin 40 years ago, and more recently by Sébastien Bergeret. And the concept is, well, in the ferromagnet, the Cooper pairs, if they want to be formed from electrons with opposite momenta, they will have to have opposite spin. They will have slightly different momenta. So you see, here's the ferromagnet, and you see this is one spin polarized band in the simplest case. The blue is the opposite spin polarized band. They're spin split by the exchange splitting in the ferromagnet. So the Fermi energy, in order to take a downspin electron and an upspin electron, they're going to have different k vectors. And this leads to a momentum-dependent or spatially variation of the superconducting order parameter in the ferromagnet. Normally in a ferromagnet, this will quench the superconductivity. Nevertheless, over short distances, the superconductivity, the normal superconductivity, the S-wave component, where the spins are antiparallel, will decrease in this oscillatory fashion. But the wave function now will have a so-called triplet component, where the spins want to be, in the Cooper pair, want to be parallel. And this will oscillate in this fashion here. So this is a very interesting concept that you introduce by proximity, superconductivity into a ferromagnet. You'll introduce some component of triplet superconductivity. Why is that interesting? Well, triplets, where the spins are parallel, in the momentum state +1 or -1, can carry angular momentum. Therefore, we could use it to manipulate magnetization. That's never actually been demonstrated, but it's something that we hope to demonstrate shortly. This is the idea then. We can introduce triplet component to superconductivity by proximizing a regular superconductor with a ferromagnet. Now, what Sébastien Bergeret showed 20 years ago was, okay, actually, if you introduce, let's say from niobium, we have a spacer layer, here is a ferromagnet, it's actually formed from the same materials we form our racetrack, cobalt, nickel layers, each one individually a few angstroms thick. The broken interfaces give rise to a perpendicular magnetic anisotropy. The magnetization is pointing up. Now, if we introduce superconductivity by proximity from niobium through copper into this material, it will follow the recipe I just showed you. However, if we introduce more magnetism by first introducing this nickel layer, which is relatively thick, in plane magnetized, what you find now is that when the supercurrent flows into this middle layer, which is perpendicularly magnetized, it can flow over longer distances. In other words, a non-collinear spin texture can sustain long-range superconductivity, which is innately triplet in character. And in these very simple experiments, these are by Ivan Kindiak, a PhD student of mine, and Swapna Mishra, a postdoc, what they've shown then is they look at this property. They look at the supercurrent flowing from an upper to a lower niobium layer, and they measure the critical current above which that superconductivity is quenched. This is shown here. And the critical current for this left side decreases rapidly with increasing thickness of this magnetic layer. However, on the right-hand side, even with more magnetism introduced by this in-plane magnetized layer, then the critical current decays much more slowly. The superconductivity proximatized into this magnetic material is more robust and will survive over longer distances. So this is very, very interesting. And what we showed is going back to this Kagome system, we showed, again, without going into much detail, we make a so-called Josephson junction. This means we have this layer shown here. I pressed the right button. This is this Kagome manganese, actually we're using manganese-3 germanium. It retains its magnetic non-collinear Kagome structure, magnetic structure to very low temperatures. Here, these blue layers are electrodes formed from niobium, which we formed on top of this magnetic, antiferromagnetic material. And we measure the current flowing from one blue electrode through this magnetic layer into the other. So what happens? This is niobium. By proximity, it induces a superconducting condensate into the manganese through germanium. And now if we pass the current, we can form a supercurrent that flows from the left to the right electrode through this chiral antiferromagnet. And what we found, and this is work by Kunrok John, a postdoc, what he did, he measured now the current as a function of voltage between these niobium electrodes, between these two niobium electrodes. And you can see for low currents, the voltage is 0. We form a superconducting current without any dissipation. However, above a critical current, you can see that the material becomes no longer superconducting, it becomes a standard resistor. And this critical current is the same, whether the current flows in the positive or the negative direction. Now, with increasing temperature, of course, the critical current decreases until the transition temperature of the proximatized superconductivity in the manganese-3 germanium. But what we find, though, is that this supercurrent can flow over long distances. We can space these niobium electrodes apart a long distance, and the supercurrent can flow through this non-collinear chiral Kagome magnetic antiferromagnetic system. So it's essentially similar to what was shown previously with these layers I showed you, which is where they're oriented perpendicular to one another. This was the first time that it was demonstrated that other types of non-collinear spin structures can sustain superconductivity over long distances. So I want to continue with this discussion, but I want to switch now to a different class of materials, and in particular, I want to discuss some of our work on 2D van der Waals metals. And in particular, I'm going to briefly introduce you to this system of nickel ditelluride. This is a so-called van der Waals system in which you can see here we have a layer of nickel shown in green, separated by layers of tellurium top and bottom, and these so-called van der Waals layers are weakly bonded to the next van der Waals layer, and in between you have a gap, basically. And these are essentially two-dimensional metals, and they can also be magnetic. This one is non-magnetic. This one is kind of boring, nickel ditelluride. It has a centrosymmetric crystal structure, and it's non-magnetic. However, it was known previously that, just as Claudia was discussing, this is a Dirac semi-metal, and it has topological spin-polarized surface states. So there is broken time reversal symmetry at the interface where we inject, or will inject, current from electrodes. So now this is just the same as I showed you, niobium through nickel ditelluride. Now we've got niobium electrodes, which we've patterned using electron beam lithography onto an exfoliated flake of this material. So you can see this is the flake. These are niobium electrodes, and they're separated by 120 nanometers, 350, and 580 nanometers. So we flow current now, a supercurrent, from one niobium electrode to the other one through the nickel ditelluride. And what do you see? You see, if we measure the voltage between two niobium electrodes, as the temperature drops, first the niobium becomes superconducting, and then at a lower temperature, the junction itself becomes superconducting. And that lower temperature decreases the greater the separation between the niobium electrodes. And on the right-hand side, then you can see now we've rotated by 90 degrees. This is the voltage. This is the current flowing between the niobium electrodes through nickel ditelluride. And of course, what you see is that depending upon the spacing, when they're closely spaced, then the critical current is bigger. But most importantly, the critical current for current flowing to the right and for current flowing to the left is identical. So we have, as usual, we have a reciprocal device where there's no difference in these critical currents for current flowing to left and right. However, what happens if we apply a tiny magnetic field, here 20 millitesla, and we apply that field perpendicular to the supercurrent? So remember, the supercurrent is flowing from here to here, this way. So we apply the field in this way, parallel to the electrodes, but perpendicular to the supercurrent. Then what you find is a dramatic effect that hadn't previously been seen. We see a diode effect. The current, critical current, for current flowing in the positive direction, you can see is of this value. But the critical current flowing in the negative direction is much bigger, 40% larger. So we see a huge asymmetry in the critical currents to suppress superconductivity. And what does that mean? That means if we choose a current in between these two values, then we'll see, and if we change the current direction, the voltage between those two electrodes will be 0 in one direction, but will be a positive value. It'll be resistive in the other direction. So this was the first observation of a Josephson diode effect. Previously, a superconducting diode effect had been discovered a couple of years earlier by Taro Ono's group in Kyoto, which itself very interesting properties. So what does it mean, and how can we understand this? As I said, this is very interesting, hadn't been seen earlier, and the superconducting diode effect would expand the possibilities of superconducting electronics, and which we think is very, very interesting. By the way, these experiments are carried out at low temperatures, 20 millikelvin in a dilution refrigerator. So we've then explored this possible model to account for this, and this is a very nice collaboration with Liang Fu's group at MIT, Margarita Daviandova and Yan Zhang were the people involved. And what they developed is a model in which you take the free energy of the system and you allow for, normally the free energy of such a system, a Josephson system, would depend on the product of the superconducting order parameters in the two materials. We can order, and that corresponds to tunneling of Cooper pairs from one electrode to the other. We can introduce higher order terms corresponding to pairs of Cooper pairs tunneling, and if we solve how the current will depend on the phase difference between the superconducting order parameters in the two electrodes, we will find, or Liang Fu finds and his collaborators, that this leads to a very interesting non-sinusoidal dependence of the current flow on that phase difference. And this automatically leads to a diodic effect, which has a particular dependence, in particular, for example, on the field. The field we apply is needed to break time reversal symmetry, which is a prerequisite for seeing this diode effect, as was broken center of symmetry in the material, which is obtained through, both cases, through the topological surface states we believe. Those topological surface states in the presence of a small field develop a spin asymmetry, and that spin asymmetry is locked through spin momentum locking, through Rashba effects at the interface, which I don't want to discuss, akin to the discussion from Claudia. The electrons flowing in this direction will develop a momentum in the perpendicular direction, and in the presence of this small field, that becomes, as I said, spin polarized, and exchange splits those states, giving rise to this triplet component of the superconductivity. From this model, you can actually work out based how the order parameter of this induced state will vary as a function of temperature, or the critical current asymmetry, how it will vary as a function of temperature. And I want to point it out that it varies in this very special fashion. It varies as the temperature is reduced away from the order parameter of the proximity-induced superconductivity in the junction. It varies quadratically. And this effectively is what we find experimentally. Experimentally, this simple theoretical model can account for this temperature dependence, and more importantly, it can account for the dependence on this perpendicular magnetic field. So in zero field, we have no diode effect. This is the asymmetry in the critical currents. As the field is increased, the effect increases, we find experimentally, reaches a maximum, then drops, goes through zero, reverses sign, and essentially oscillates as a function of increasing field. And this is exactly what you can find from this very simple model. This can account for this dependence that we observe. So this very characteristic field dependence and temperature dependence can be accounted for through this finite momentum Cooper pairing induced by, we assume, the spin polarized topological surface states through Rashba effects. So it's really a very interesting phenomenon. I don't think I want to discuss this in detail. I might be running out of time, but probably 5 minutes, okay. So I have to hurry up. I just wanted to say that this model then, this is our experimental data. What we're doing now is we're rotating a fixed magnitude of field away from the direction perpendicular to the supercurrent, where we have maximum asymmetry, goes to zero when the field is parallel to the supercurrent, changes sign when it's in the opposite direction. You see this is the dependence, and as a function of magnetic field, and this is what we see theoretically. So I'm not going to discuss that. I've briefly introduced that model. So this is why we're interested. So coming back to Racetrack, what do we want to do? We haven't demonstrated it, but we imagine that this diode effect can be a very interesting way to detect magnetization at these millikelvin temperatures. We get a big signal or a small signal depending on the orientation of the magnetization in the domain with respect to this diode effect. At the same time, we can imagine by creating these triplet currents, we have lots of ideas, these triplet currents could carry angular momentum and enable us to move these domain walls very energy efficiently. This is something that we are currently working on, haven't yet demonstrated. So I want to just briefly then discuss, there's no time, but briefly, very interestingly, we don't need to use nickel ditelluride, which is a very exotic material. Let's go back to a very basic material. We take platinum, and we do this. We make a platinum layer, it's roughly 10 nanometers thick, by sputtering onto YIG. YIG is a garnet, it's an insulating material, has a very complicated structure, it's a ferrimagnet, nevertheless, it has a net magnetization. So we apply a big magnetic field to magnetize it in one direction, zero field, there's a magnetic moment, and that magnetic moment is imprinted into the platinum layer. So the platinum film at this interface becomes magnetic by proximity. And at the top interface of platinum, Just as for the nickel ditelluride, we build a Josephson junction here using niobium layers. And now we flow supercurrent from one niobium to the other through platinum. Well, the platinum becomes superconducting by proximity, and the platinum is magnetic by proximity to the lower substrate. Through two proximity-induced effects, we can build a Josephson diode. And this then is super interesting because this type of material we can directly integrate into Racetrack, which I mentioned uses a platinum layer for developing spin current through the spin Hall effect. And what do we see? Reverting again, the orientation of these signs, we see again that the critical current, this is the current flowing between those niobium electrons through the proximatized platinum into a magnetic and superconducting state, and we find now that the critical current for superconductivity has a large asymmetry between left and right motion, which we can reverse by simply magnetizing the yig in the opposite direction and going back to zero field. Here we can then see in zero field a large Josephson diode effect. And by the way, these measurements are taken at 2 degrees Kelvin, not at millikelvin temperatures. And the size of this, the diode efficiency, the difference in critical currents, left and right, is 40%. In the case of nickel ditelluride, maximum effect we could see was up to 80% at these 20 millikelvin temperatures. Here, we're just operating at 2 degrees Kelvin. And we can also look at the temperature dependence. Now, it turns out the temperature dependence has a different temperature dependence from nickel ditelluride. It has a square root dependence on temperature. So this is really interesting, and I don't have time to discuss that. But we find then that, the temperature dependence of this reciprocal effect, we find in one case, this is our previous work I mentioned to you, nickel ditelluride, we have this quadratic dependence on delta T. This is a theory by Nagoso and company, basically got the same result we found with our collaboration with Liang Fu. And this is our measurements on platinum. And there's another paper also by Nagoso who calculates using a different theory, gets the same temperature dependence we see here. So this temperature dependence is really, really interesting. And I see I'm running out of time. So just in the last 1 minute, I wanted to mention that we've now used exfoliation to build a true 2D Josephson junction where current flows from the top to the bottom from a niobium diselenide layer, we've exfoliated, it's a 2D superconductor, through tungsten ditelluride, which has broken crystal, it's not centrosymmetric, it's actually orthorhombic. And why is this interesting? So now we flow the supercurrent from niobium diselenide through tungsten ditelluride, and the current flows vertically. And now in the plane of the tungsten ditelluride, we have to apply a magnetic field to see the diode effect, but now we can change the direction of that magnetic field with respect to the tungsten ditelluride orthorhombic crystal structure, and we only see a diode effect when the field lies along a particular crystal direction in the tungsten ditelluride, confirming the intrinsic origin of the diode effect is related fundamentally to the properties of the tungsten ditelluride. Since I'm running out of time, I'm going to just show you this. We basically see a beautiful variation of the diode efficiency as we need a magnetic field, a small magnetic field, as we rotate that with respect to the crystal structure, intrinsically proving the intrinsic origin of the effect. So let me come to my conclusion foil, since we don't have more time to discuss. Well, anyway, and then, this is all, basically this is our work. But in conclusion, the diode effect we've now seen in all these different Van der Waals materials in magnetized platinum. And we think this is a very interesting effect and could be used to manipulate these domain walls in Racetrack to build what I call supermint, a cryogenic Racetrack memory that could support quantum computing systems which require low temperature, high performance memory and logic devices at those temperatures. Thank you very much for your attention.
May I use these microphones? Okay, now we have time for a couple of questions, please. Judith, please.
Stuart, you started out with your lovely magnetic racetrack, which you worked on for 20 years.
Yeah.
But then you moved to something much more exotic.
Yeah.
And that is trying to control it at cryogenic temperatures, because is that because you're saying that actually it won't work at room temperature?
Oh no, it works at room temperature. So we have a project with Samsung. We've worked with them now for 5 years. They support research for us to demonstrate the shrinking of racetrack to dimensions that are technologically relevant. I just showed you at the very beginning, we've been able to do that. We've been able to demonstrate the motion of domain walls in racetracks just a few nanometers wide.
Is it a challenge of trying to control the current, so really control those domain walls very carefully? Is it?
No, we think now we totally understand the motion, and we can position the domain walls, as I mentioned, to an accuracy of a few tens of nanometers. This is sufficient to build a very interesting racetrack memory technology.
But those domain walls, I mean, the whole structure's very fiddly, isn't it? You've got
No, it's not fiddly. It's perfect.
Scale. You've got one atom, layer. Thick.
Yeah.
It has to be really perfect to.
No, it doesn't have to be perfect. It has to be nearly perfect, but not absolutely perfect. So in other words, you're totally right, but let's say we take a spin valve sensor that is used in all the disk drives manufactured in the world since 1997, that uses a ruthenium layer which is 7 angstroms thick. It uses interfaces layer of cobalt 1 or 2 angstroms thick, already used.
You're talking about 1 angstrom thick in
Yeah. 1 angstrom,
different.
1 to 2 angstrom. So here I'm talking, what's the difference? It's the same, right?
Okay.
No, we're super interested in racetrack. No, we believe we can go beyond. We've demonstrated room temperature racetrack and above is totally possible.
And in your Josephson diodes, reproducibility interfaces are always fine?
Well, you can't say always, but
Occasionally.
it seems to be very robust, I would say. So it's surprisingly so, and surprisingly common to many different systems. So this is real surprise that like 3 or 4 years ago, no diode effects except extrinsic effects from current passage effects, artificial geometrical effects. Now we've seen intrinsic effects.
Then you move to using platinum, but to
let other
make that-
people
Oh,
ask
sorry.
questions. Okay. Yeah, discussion can be a little bit later. Anyone else wants to ask question? Please do.
Oh no.
Oh, now I regret interrupting this discussion. May I allow myself to ask a question? I wondered, it's not a tricky question, okay, but I couldn't answer myself. Okay. When you move domains by current and your whole sensor, or whatever sensor you can, magnetic field sensor is static. What is the advantage rather than having a static domain structure and move the whole sensor?
Oh, so that's like a magnetic disk drive is what you're describing, where you mechanically move a sensor.
Yeah.
And that takes a huge amount of energy and is totally unreliable. Today's magnetic disk drives, the sensor is 1 nanometer above the surface of the magnetic field during operation.
That's what
and
I'm
it fails.
saying.
It fails very often. This will be totally reliable. Also uses a huge amount of energy to move that device, mechanical device. And it's very slow. Maximum speed, 10,000 revolutions per minute. A few milliseconds to access the first data bit.
You're saying that speed is quicker than rotation of the disk, and energy on mechanical rotation is higher than energy
very high.
rotation.
So much less energy. You don't need to rotate a mechanical object to read 1 bit.
But
what?
But joule losses are in your system probably also non-negligible.
They're negligible. It turns out in all memory systems today, most of the energy is consumed in capacitive charging of wires. This has been true for 10 years. So the actual amount of joule energy we consume will be very little compared to these other energies.
Okay. Any other questions? If not, let's finish the session nearly on time. Thank you.